Technologies. So, optimizing conditions. How do we optimize conditions? This is something that they love to ask about because it's something that comes up in industry. So even if you're not thinking of becoming a chemist in the future, if you're thinking of going into an industry of any kind, you want to optimize your conditions. You want to make sure that you are producing as much of your product or creating as much of you want to create without wasting time, money, effort, resources, etc. So specifically within chemistry, as I've mentioned a couple of times, temperature is the thing that can change the value of Kc permanently. Whether Kc will increase or decrease with a change in temperature depends on whether the forwards reaction is exothermic or endothermic. So if you change the concentration, you don't change the value of Kc. The position of equilibrium will adjust to get Kc or to keep Kc constant. It will adjust to allow your ratios of reactants and products to settle back into the values where Kc is constant. Change the temperature, it will change, but it is dependent on whether you've got an exothermic or an endothermic reaction. And, funnily enough, the effect of this can be predicted with Le Chatelier's principle. Now, here we've created a table. So if you are the kind of person who really likes learning things off by heart and has got a very good memory, feel free to learn this, but I would highly, highly recommend that you understand it as well. Because if you don't understand where these things come from, you won't be able to apply it to a new context. So please, please, please do try and understand it if you can. So, optimizing conditions. If we are to increase the temperature and the force reaction of our equilibrium, of our dynamic equilibrium is exothermic, then what's going to happen to delta H? Or what is delta H? Delta H, if it's exothermic, delta H is negative. What's going to happen to Kc? And what's that going to mean in terms of the position of equilibrium? Where is our position of equilibrium? So if we increase the temperature and the forwards reaction is exothermic, that means the backwards reaction is endothermic. Kc is products over reactants. Products over reactants. Concentration of products over concentration of reactants. If it's exothermic, it's giving off heat. The forwards reaction is giving off heat energy or giving off energy. So if we increase the temperature, Kc is going to try to, or the position of Kc is going to adjust to decrease the temperature again. If it wants to decrease the temperature, it's going to need to go against the forwards reaction because that's also creating heat and increasing the temperature. So it's going to shift the position towards the reactants. It means the reactants are favored. So position of equilibrium is shifting to the left to bring the temperature back down again. So if our reactants are being favored, they're on the bottom of the reaction. If the bottom of the fraction is getting bigger, sorry, fraction, not reaction. If the bottom of the fraction is getting bigger, the value of Kc, if you think about the bottom of a fraction getting bigger, that means the fraction itself is getting smaller. So changing Kc is going to decrease. Kc is going to decrease. And vice versa, if we increase the temperature and the forwards reaction is endothermic. If the forwards reaction is endothermic, that means delta H is positive or it's taking in energy. It takes in heat energy. Should have put an energy there. What's going to happen? Well, if we increase the temperature, it's going to want to decrease the temperature again, which in this case is going to involve more of the exothermic direction, which is the backwards direction. No, endothermic, sorry. We're increasing the temperature. We're going to try to start again because my sentences are getting lost. The forwards reaction is endothermic, which is positive, so it's taking in heat. If we increase the temperature, it's going to continue to want to do the forwards reaction to take in more of that heat that we've been adding. So the products are going to be favored. Products are favored. Looking at our fraction, if the top of the fraction is bigger than the bottom of the fraction, or sorry, if the top of the fraction is getting bigger, I shouldn't say is bigger than, it's getting bigger, that means the value of Kc is going to be getting bigger as well. If the top of a fraction is getting bigger, the whole fraction itself is getting larger. So we are getting an increase in Kc. And funnily enough, it's vice versa for the others. I'm not going to go through that because you can work it out yourselves using the same principles. I would highly recommend that you understand it. Don't just memorize that table, because you will find it difficult to apply it to new contexts if you're just memorizing it. So try to understand it if you can. Okay, what happens when we try to optimize conditions though? Because lots of the time, high pressure or high temperature is what we want in terms of pushing something towards and then shifting the equilibrium towards a product, perhaps, or speeding up the rate of the reaction with a high temperature, for example. But why is this an issue? Well, high pressure and high temperatures is not always useful because they are difficult to maintain, and therefore also require specialist equipment. High pressure gases require specialist equipment, so are not suitable for every industry, for every company. It can be maintaining high pressures and high temperatures can be expensive, lots of energy and new equipment required. And if there are high energy, it can be expensive in terms of, power input needed. Also, high temperatures and high pressures can be dangerous. So again, as well as needing new specialist equipment, you can have quite a high risk there. So potentially dangerous. I'm going to put potentially, actually. Potentially dangerous. Low temperatures, therefore you might think, well, let's just do it with a low temperature then always. But low temperatures can often mean that you have fewer collisions, and fewer of those collisions are successful. So you have a slower rate of reaction. That means it could take ages for a product to be produced. So lower temperatures aren't always the answer, because you have can have lower rates of reaction. So what else could we do? We can have catalysts. We can add in catalysts. That means the equilibrium was reached faster, but the position of equilibrium is unchanged. That's a lovely, that final point, they like to ask in exams or test. So don't just remember, with a catalyst will speed up both directions of the reversible reaction. So if we're in equilibrium, we know we've got a forward and backwards reaction. Catalysts speed up both directions by the same amount. So you don't have a moved position of equilibrium, but you get to equilibrium faster. So it is useful to have catalysts, but not if you're trying to kind of increase the yield of a product, perhaps an overall yield of a product, or you're trying to push the position of equilibrium in one direction, because it'll change both. It pushes both in the same by the same amount. So you get no change, no overall change.